Hello everyone, this is Puya. So in this video, we're going to talk about the concept of polymorphism, virtual functions, and abstract classes in C++. This is continuation of what we did in the videos about inheritance. So let's do a review. Let's just first look at the meaning of polymorphism. Poly means many, morph means shape. So basically the ability to assume different forms or shapes is the meaning of polymorphism, or the conditions of occurring in several different shapes. So that's what polymorphism is, like basically something that can assume different shapes or different forms. This is what the meaning of polymorphism is. Now, this is a review of what we did in the previous video about inheritance. We have a base class, a derived class, which is derived from the base. Now we instantiated an object of base and instantiated an object of class savings. Like this is the parent, this is the child, or super and subclasses. Now here the object of class base, it's calling the assignment operator, which the compiler is going to generate, to assign an object of class savings, which is derived from base, to it. This is a valid operation. This is possible. This is called a slicing. We basically slice part of S that's common, like it means that only the part that has ID and balance, and assign the ID and balance of S to B. So this is what's happening here. Again, I should emphasize that here we are using the member variables as public only for simplicity. Usually in object-oriented programming, we want to have our member variables as private, so we want to have data hiding, right? So this is only for simplicity. However, the other version is not valid because the object of class base cannot be cast as an object of class savings. It does not have everything that class savings objects do. So class savings object, they have ID, balance, age, and ATM, right? But class base objects only have ID and balance. So we can't just assign B to S. This is going to lead to compiler error. Similarly, we have the same story for pointer variables and reference variables. So you see here, then again, like B is an object of the superclass, S is an object of the subclass. B equal to S is a valid operation, however S equal to B is invalid. And if we have a pointer of type base star, right, it's a pointer, it's going to point to an object of class base, and we have SPTR, which is a pointer of savings star. It means that it's going to point to an object of class savings. The base pointer can point to an object of class saving because this object has everything that base objects do, right? It has ID and balance, right? So this is possible. This is a valid operation. However, SPTR equal to ampersand B or address of B, this is not a valid operation. You have to keep in mind, so this is the main point of this lecture, that this BPTR, the way we defined it, it's a base star variable. It's a pointer to a base object kind of variable. Okay, so it does not have access to age and ATM of S, right? We call this early binding. So this is like, because BPTR is of type base star, it doesn't have access to member variables of class savings. So although BPTR can point to S, but we cannot have access to age and ATM members of s through bptr. Okay, so if you try to say, like, for example, cout bptr arrow h, that's going to be an error, right? So this is something that we're going to see more about in this lecture. Same story about reference variables. So if bref is a reference variable of type base, like reference variable, so like you can assign an object, so you can just like basically you can have a nickname for it as s. So like this one, this is possible. You can have a reference variable bref that's gonna be assigned to so that s is going to be assigned to it. And the other way around is not possible. So you can't say savings ampersand sref equal to b. That's going to be invalid. This is valid, the other one is not valid. So you have to pay attention to this part. This is going to be the whole point of this lecture. So when we do this, when we assign an object of the derived class to an object of base class, we are basically doing a slicing. You remember that the child class is always bigger than the parent class. It has everything that the parent does. In addition to that, it has extra member variables and member functions, right? So when you assign D to B, you're basically cutting one slice of the derived object and assign it to the base object. This is called a slicing problem. Now look at this example. So we have a class base and we have derived two subclasses, savings and current, from class base. Class base has two member variables and a member function called print_info. The savings has two extra member variables. We have redefined the print_info member function inside class savings. The same story for class current. We have redefined the print_info member function in class current. Now let's look at this. Base star bptr, bptr is pointing to s, bptr is assigned to address of s. Now we say bptr arrow print_info. bptr is a pointer pointing to a savings object. But when I use the bptr to call the print_info, because bptr is a base star kind of variable, base asterisk kind of variable, it's gonna call the print_info function of the class base. It's not gonna call this one, it's gonna call this one. This is called early binding. Okay, we say that because base, we define base bptr as a base star variable, right? So when we say bptr arrow print_info, it doesn't matter what bptr is pointing to. It doesn't matter if it's pointing to an object of class savings, an object of class current, or an object of class base. It's always gonna call the print_info from the class base. This is what early binding means. Like, it's always gonna call this one. It doesn't matter what it is pointing to. Okay, the same story for this case. If bptr is pointing to an object of class current, and if I want C to call print_info, but I'm doing it through the bptr, so if I say bptr arrow print_info, it's gonna call this one instead of this one. Okay, so this is early binding. So we want to know like what the solution for this is. Like, how can I make sure that when bptr is pointing to an object of class S, when I say bptr arrow print_info, what should I do so that this function would be invoked instead of the base member function? So this is what polymorphism is. Like, this is like how we can solve this problem. The solution is by adding a keyword in the base class member function. That keyword is virtual. So defining the print_info as a virtual function. Once you just add this keyword, you're letting the compiler know that if you have a base pointer, or if you have a base reference variable, if they call the print info function, right? You have to, like, the compiler is gonna check what is BPTR is pointing to. If it is pointing to an object of class base, it's gonna call this function. If it is pointing to an object of class savings, it's gonna call this function. If it is pointing to an object of class current, it's gonna call this function. So this is called late binding. It means that now, like, if you just look at this line, if you just look at this red line, you can't say, like, if you ignore the rest of it, if you don't have like access to the rest of program, if you only look at this line, you don't know which function is going to be called. It depends on what BPTR is pointing to. If it's pointing to an object of class base, it's going to call this one. If it is pointing to an object of class savings, it's going to call this one. If it is pointing to an object of class current, it's going to call this one. So this needs more complexity for the compiler, because it has to figure out what BPTR is pointing to. So there is like some additional time needed for the compiler to figure this out. If we didn't have this virtual function, virtual keyword similar to this, if you just look at this line, it's always going to call this one. Like, doesn't matter like what BPTR is pointing to. But by just adding the virtual keyword before the member function, we just like provide polymorphism. So basically this line can act in different shapes, can can assume different shapes. It might call this function, it might call this function, it might call this function. The same story is going to be valid if this was a reference variable. So if you had, for example, base ampersand bref equal to s, if you say bref dot print info, now it's going to call this one instead of this. The same thing is true for reference variables. So in C++, polymorphism is happening when you have a pointer of the base class that's going to point to an object of derived class, right? Then in that case, when through that pointer you're calling a function that has been redefined, right, assuming that you have the virtual keyword, then it can call the corresponding member function from the correct class. Okay, the same thing is going to be valid if you have a reference variable. Okay, so when you have a reference variable of the base class, if you use that variable to call a member function that has been defined, a virtual member function that has been redefined, then you just have to know that what reference, like what type of object that reference variable is referenced for. Okay, so that's what the concept of polymorphism is. One thing that I have to mention here is that many programmers just use the virtual only for the base class, but you can also like put virtual for the subclasses as well, right? So like if you see in one program that like all of these functions they have virtual, that's okay. The only one that's mandatory is this one, but it's a good practice to put virtual here so that like everybody who looks at this class knows that this has been this function is redefined, and just like the class base has a similar member function. So let's look at this example, right? Let's look at this example. Okay, so this base class has two member function. One is call, one is print info. One is not virtual, one is virtual. And these two functions have been redefined in the class savings and class current. Now, if BPTR is a pointer of type base, of type base star, it's pointing to a savings object. So if BPTR holds the address of an object of class savings, if I say BPTR arrow call, because this is not virtual, this is going to be early binding. It doesn't matter like it's pointing to an object of class savings. It's always going to call the base call function. Okay. However, for the print info, it's going to call the savings print info function. Late binding. It looks at BPTR and it looks at like what object it is pointing to. Okay, because it's an object of class savings, it's going to call the print info of class savings. The same story here. Okay, all the examples we have here are for pointer variables, but the same story is true for reference variables. Okay, this is another function here. So you can see that here the print info is virtual. Okay, and the print function is calling the print info. Okay, because and here like we don't like, yeah, we have print info is a virtual function. Okay, so if we have a base object, a savings object, and a current object, b.print, it's gonna come here, right? It says like call the print info. It's gonna call the base print info. But s.print calls the print info from savings. c.print calls the print info from the current. Okay, so if you think about it, like here, the this arrow, the this pointer would just like basically this is virtual, right? You actually like you're calling the print info using the this pointer, so it's gonna call the corresponding print info function from the right class. So this is when you use virtual function, you have to define each virtual function before compiling. Okay, so like you have to make sure like this is like declaration is not just sufficient. Even if you do not call the virtual function, you may see error message. So you have to make sure you have the full definition before compiling, because the compiler needs to know, like when you have a virtual function, it needs to know what function to call when you have virtual. So like there's more work for the compiler basically, because there's not early binding anymore, it's late binding. This basically summarizes this. So you just like add a virtual keyword to function declaration in the base class. Virtual is not needed for the function declaration in the derived class, but is often included. Virtual is not added to the function definition. So if you just declare the function inside the class and you put virtual, when you define it outside the class, you don't need to provide you shouldn't provide the virtual keyword. Virtual functions require considerable overhead time. So excessive use reduces program efficiency, because the compiler has to do more work. It has to figure out which function to call. Virtual functions whose definitions are changed in a derived class are said to be overridden. Okay, and non-virtual functions whose definitions are changed in a derived class are redefined. So like overridden and redefined, these are technical terms that are used. Okay, so here we say that call has been redefined, but print info has been overridden. It's just like technical functions, technical terminologies. This is another example that shows like how basically polymorphism works in this case. Here you have early binding. So if this pointer, even though it's pointing to a derived object, it's going to call the function 1 from the base. But if once you add the virtual keyword, then it's going to call the function 1 function from the derived class. This shows like what I mentioned about early binding and late binding, or also called static binding, early binding or static binding, or dynamic binding or late binding. Okay, so you can think of it, this example basically shows you that, like, let's say, like, um, you, you know, like three different like recipes, three different recipes to cook, and if I ask you to make one of those, then you can just easily do it, right? But if you participate in a cooking contest, right, they're gonna give you like something new, right? So you have to think about how to make that possible using what you have available. So there's more work needed when you do late binding for the compiler. So that's the concept of binding. This is an example using pointer and I think only pointers, and also like this is also gonna be another example that you can just analyze this code and see what's gonna be printed on the screen. This can show you like what late binding is and what early binding is. So here for the print we have a virtual keyboard, but for the show we don't. Okay, so similar thing is happening here, so we can analyze this code. This is another example. So many times in programs, like we would just like have one super class, let's say class shape, right? And then we might have some virtual class like draw or area or circumference, or like many different things. So these classes, subclasses are derived from class shape, class line, class circle, class square. Okay, and the function draw is a virtual function, right? So like you just like have a pointer, depending on what kind of object that pointer is pointing to, it can call either this function, this function, this function, or the shape class function. Now let's look at this example. This is an interesting example. It shows you the motivation for something called virtual destructor. So if you guys remember, like we mentioned that constructors are called from top to the bottom, and destructors are called from bottom to the top. Constructors are from parent to the child, and destructor from child to the parent. So now let's look at this one. We have a star aptr. So we have a pointer. Like, first of all, we have two classes. Class A, which is our base class, it has a constructor and a destructor. Class B, which is derived from class A, okay, it has a default constructor, it has an additional member variable, has a default constructor, and it has a destructor. Okay, so a star aptr, this is a pointer, just gonna point to an object of class A. Now aptr is equal to new B, so we are allocating an object of class B dynamically. Okay, so aptr is going to point to an object of class B, right? So now this new object, which is going to be star aptr, this is going to call the constructor. Okay, it's going to go to the constructor of the derived class, but before enters it, it's going to call the constructor of the base class. So it's going to print A. That's what we see here. Once this is done, now we can enter the constructor of the derived class. So once it goes here, now this object, this new object that has been allocated, has a pointer that's going to point to an integer called z, right? And we say that this z is now going to point to a dynamically allocated integer. Okay, dynamically allocated integer. Anything that's dynamically allocated, we have to make sure to deallocate it. Otherwise, we would have memory leak. So this is done, and then it prints B. That's what's happening here. Okay, then in the next line, it says delete APTR. Okay, so it says delete APTR. APTR is pointing to an object of class B. But because APTR is of type A star, it's gonna call the member function of the class A, right? This is early binding. We are deleting this object through APTR. This is early binding, right? So it's gonna delete that object. But what happens to this dynamically allocated integer that Z was pointing to? Now that we delete that object, still Z is gonna remain in the memory because we were gonna delete it in this destructor, but this destructor is not called because we deleted through APTR, and APTR is of type A star, and because of that we have memory leak. So like whatever member variable, whatever dynamic memory we allocated here is gonna stay in the memory. It's gonna occupy the memory. What is the solution for that? So the solution for that is to convert this one from early binding to late binding, from static binding to dynamic binding, right? So we want to make sure that when we do delete APTR, it's gonna call the destructor from the class B because APTR is pointing to an object of class B. Can you guess what the solution is? Yeah, just like adding a virtual keyword before the destructor. This is called virtual destructor. So once this happening, the constructor part is similar, 1, 2, 3, and then 4. So it prints A and B. We have APTR pointing to an object of class base. Inside that object, we have a pointer, an integer pointer that's pointing to a dynamically allocated integer. Now it says delete APTR. Because this is virtual, this is late binding, this is polymorphism. So it has to look what APTR is pointing to. It's pointing to an object of class base. So it's gonna call the destructor from base, right? So it's gonna finish this one. It's gonna delete that dynamically allocated integer. It's gonna print tilde b as well. And you remember that once the destructor for the child class finishes execution, it's gonna call automatically the destructor for the base class. So it's gonna print tilde a at the end as well, right? The constructors go from top to the bottom, destructors go from bottom to the top. Okay, so that's the concept of virtual destructor. Especially if you have dynamic memories, it's very important to pay attention to it, especially if you want to do things using like a base pointer, base class pointer. Now, so we talked about polymorphism, early binding or static binding, and late binding or dynamic binding. Also talked about virtual functions and virtual destructor. Now we're going to talk about another concept called abstract class. So an abstract class is a class that we don't want to instantiate any object from. It's kind of weird, right? Why do we want to have a class that we wouldn't instantiate any objects from? We're going to use that class only for the sake of inheritance. So abstract class is where you just like, let's say that bank account example we did, right? So we can define that bank account as an abstract class because like anybody who wants to open a bank account, it's either going to be checking, savings, deposit. It's not just going to be purely a bank account, right? So like an abstract class is a class that we define only for the sake of inheritance, so that like we put all the common member variables and member functions in it, and we do not instantiate any objects of that class directly. Okay, how can we make a class abstract class? You just have to have something called pure virtual function. So if a class has at least one pure virtual function, then the class is called abstract class. I'm going to talk about what a pure virtual function is. Okay, when do we use it? When using the base class directly has no meaningful purpose. Let's say like you want to write a database for cars, like for an auto dealership. Uh, right? So like you just like, let's say like you have an abstract class car, and then subclasses would be different different makes, right? So like Honda, like Hyundai, Toyota, Porsche, and etc. You don't have like any car with just like no brands, right? Like with no makes, right? So this is like with using the base class directly has no meaningful purpose. It just like makes sense to use it only as a derived class. So only like use the derived class, and everything that was inside the base class, which is an abstract class, is going to be inherited by the derived class. So example was the bank account that we already mentioned, like cars, shapes, for example. Different examples can be mentioned here. Okay, so what is a pure virtual function? So let's look at the same example we had before. So now we have the same class. A pure virtual function is just a virtual function that has no definition in the base class. We just say virtual void call, and then like there is no definition, equals 0. By adding this equals 0 and putting a semicolon after it, we make this one a pure virtual function. If a class has at least one pure virtual function, it is an abstract class. It means that you cannot instantiate any object of this class directly. So if you try to say base B, that's going to give you an error, because it says that this is an abstract class. You cannot declare objects of class B, which is an abstract class type. Okay. Now, one other thing that you have to be careful, any pure virtual function that has been declared in the base class has to be redefined in the derived classes, right? Because this one has no definition, right? So every purely virtual function has to be redefined in the overridden in the derived classes. So like you can see that here call has been excuse me, overridden here. The same thing here, print info. Okay, and this class savings, it inherits ID and balance, and like you might have like more member variables or other member functions. They don't have to be not all of the functions have to be purely virtual. Only if only you have one purely virtual function, that class is going to be abstract class. Okay, so now let's look at this one. This is important. You can't instantiate any object of class base. You can have pointers of that one. You can have reference variables of that one, but you can't instantiate any object of class base. Okay, so now in this case, B arrow call, B is pointing to an object of class savings. B arrow call is going to call this one. B arrow print info, it's going to call this one. If B is holding the address of C, B arrow call is going to call this one. B arrow print info is going to call this one. This is called pure virtual function. You can see another example here, the class base. Okay, it has one pure virtual function and it has one regular function called set balance, right? So all these two subclasses, they would inherit ID balance. Also, they inherit set balance. You see, set balance has not been redefined here. Okay. But however, the get interest has to be overridden here because this is a pure virtual function. Okay. We can't instantiate any object of this class, right? We can instantiate objects of the other class. And this basically shows you an example of this example of purely virtual function. An abstract class is a class that can be used only as a base class of some other class. No objects of an abstract class can be created except as sub-objects of a class derived from it. Note that abstract classes can have constructors and destructors like other classes. So although you cannot instantiate any object of this class, but you can have constructors and destructors. What are they used for? They are going to be called by the derived objects. You remember that the derived objects, whenever is instantiated, it's going to call the constructor of the base, then goes to the constructor of the derived. So they are called by the objects of the derived classes. That's like one common mistake for new programmers. They think that like the abstract class cannot have a constructor. It can have a constructor. It can have a destructor. This shows like more like examples. Like let's say like you can have an abstract class of polygons and triangles, and like a trapezoid, for example, as subclasses. You cannot create objects of abstract class. You cannot instantiate objects of this class. Used when the base class is only meant for inheritance, for derivation. Helps in readability and understanding the code, and prevents accidental instantiation of abstract class. Okay. Like the next few slides shows you an example of writing a program that finds the past tense of some verbs. Can be regular or irregular. So this can be an abstract class. This is like subclass. This is another subclass. Like here you see the solution for that. I'll just leave it up to you to look at it. Okay, so this also like shows the output, a sample output. Another example here. So like here I'm using both pointer variables and reference variables, or sorry, no, it's only pointer variables. So I'm only using pointer variables to show you the concept of purely virtual function, abstract class, and overriding function. This one, it's like almost an advanced topic. So, but like I am just gonna mention it very briefly. Let's say that we have a base class and we have a derived class derived from it. So you remember that a base pointer can point to a derived object. That's okay, right? So this is automatic casting, upcasting. So this object is going to be upcasted as a base object, right? So this is possible. So we have two pointers. Both of them are of type basis star, but one of them is pointing to a derived object. The other one is pointing to a base object. And we have another pointer which is of type derived pointer. Okay. Now let's look at this one. I want to assign PBA to PD. This one is base star, this one is derived star. But let's look at PBA. PBA is pointing to a derived object. Okay, so I can dynamically cast PBA to a derived star pointer. So this is possible, right? Because PBA is originally pointing to a derived object. Okay, this is called downcasting, right? You're casting a base pointer as a derived pointer. Okay, this is a base star. It's casted as a derived star. This was only possible because PBA is already pointing to a derived object. However, for PBB, for this variable, we can't cast this as a derived pointer. Why? Because it's pointing to a base object. So this is going to cause an error. Okay, basically PD becomes 0. Not an error, like, but this is not successful. It's unsuccessful downcast, so PD becomes 0. Okay, this is like successful downcasting. This is unsuccessful downcasting. When dynamic cast cannot cast a pointer because it's not a complete object of the required class, as in the second version in the example, it returns a null pointer. Sorry, so it doesn't cause an error. It just like returns a null pointer so that you know that there was a failure. So this explains like the concept that I just mentioned here. So we can just read through it later. Some remarks about polymorphism. So late binding or dynamic binding comes at the cost of performance penalty. So like it takes longer for the compiler to compile the code. Remember that static functions cannot be overridden. Okay, so static member functions cannot be overridden. Pure virtual destructors also exist in C++. Okay, so we said that you can have virtual destructor, you can also have pure virtual destructor. But we don't have anything called virtual constructor, right? We have virtual destructors, but we don't have virtual constructors, so keep that in mind. This basically summarizes everything that I mentioned through this video. It's like application of polymorphism is the ability to reuse and extend the code, just like having a base pointer or base reference variable, and you can just like have like different forms of operations using that pointer or reference variables. It means that you have the same code act differently depending on the context, depending on like what that pointer is pointing to or what that reference variable is reference to, depending on if you have virtual functions or not. In terms of programming, this means that you have the same function in different contexts. C++ polymorphism means that a call to a member function will cause a different function to be executed depending on the type of the object that invokes the function. Polymorphism saves the program a lot of time in recreating the code. You don't have to write completely different modules for every possible scenario. Polymorphism allows you to create a pointer to a derived class which is also compatible with the base class. Polymorphism is generally used where you have different classes with a function of the same name. Like for example, you have like a abstract class shape and many subclasses. Each of these functions might have the same function area or circumference or draw or like other things. So, and even the same parameters but with different implementation. A virtual function is a function in the base class that's declared using the keyword virtual. Defining a virtual function in the base class with another version in a derived class signals to the compiler that we don't want to have static linkage, static binding, static linkage, or early binding for this function. Pure virtual functions, it is also possible that you want to include a virtual function in a base class so that it may be redefined in a derived class to suit the objects of that class. but there is no meaningful definition in the base class, right? If you have an abstract class shape, what's the area of a shape? Do you have a formula for area of a shape? No, it doesn't have any meaning. So it doesn't have meaningful definition you could give for the function in the base class. So if a class has at least one pure virtual function, the class becomes an abstract class. Some exercise for you here. I think I was asking you to look at this code that's given, and based on like what is provided here, you're supposed to make some changes to it. I'm asking you to analyze this code and answer the questions. What happens if you replace the function with this function? What happens if you replace it with this one? To practice polymorphism. Another example for polymorphism, what happens if we remove the virtual keyword? You can see that here, like we put virtual in both base and derived class. That's okay. What do we need to change so that we get this output? And this is a very good project for people who are interested in doing extra work. So write a program that takes a string, and that string is a mathematical expression, right? It can have different operators, right? And then you return another string that would be the derivative of the original string. So for example, you would just like call a function with the string like x squared plus 2x, and then your function, and like you also specify the parameter x, for example, and then your function is supposed to return another string which would be the derivative of the original expression, let's say 2x plus 2. Okay, so this is a good project for people who are interested in more advanced programming. Okay, thank you so much. That was it for polymorphism.